Okay, so good evening, everybody. Welcome to the Asset Colloquium. And some of you probably who are joining from outside the TIFR family, let me introduce what ASSET is. ASSET stands for Advances in Science, Engineering and Technology. This is a forum of TIFR which organizes colloquia every Friday at 4 p.m. Now, of course, online. These talks or these colloquia are mostly centered around the detectors, the instrumentation, electronics, the software, and some of those fields, which essentially complement the other areas which are covered on Wednesday by the Wednesday Colloquium or NSF Colloquium. NSF stands for Natural Sciences Faculty. And on Thursday, we have such colloquia from mathematics faculties. So this is a colloquium essentially dealing with the instrumentation and electronics. So hence the name ASSET. And very aptly, today we have Professor Yashwant Gupta, Center Director, NCRA facility of TIFR Pune, going to give the talk, which is titled as From Kalyan to Khodad and Beyond, the Milestones in the Growth of Radio Astronomy at TIFR. Before even I say anything further, I would like to take this opportunity on behalf of the TIFR, of course, in particular, but also the entire country, I must say, and you'll realize why I said this, to congratulate him and the team GMRT. They have just a week ago, they were given a fantastic honor by the world's largest professional body called IEEE. IEEE, of course, many of you know, it's one of the oldest and the largest professional body, about 136 years old. It has about 430,000 professional members, and it's a great organization. And IEEE has recognized the GMRT as one of its what they call milestone in electrical engineering and computing. In just to put this honor in perspective, I would like to say the only other two such facilities or discoveries or inventions in India that were recognized by IEEE is the first one, Sir J.C. Bose's demonstration of generation and reception of radio waves way back 1895, almost as old as IEEE, and the Nobel Prize winning work by C.V. Raman way back in 1928. So in a way, this honor comes almost after 90 years of just the previous one. So that really makes this a big honor. And as I said, we are very, very happy. And at the same time, we would like to congratulate all the great work that was done by Professor Yashwant Gupta and his predecessor. Of course, we cannot forget Professor Govind Swarup and the entire team of GMRT. In fact, what ASSET is actually planning, in fact, it has planned much before the news came about to have a series on GMRT, particularly because over the past few years, an extensive hardware upgradation of the GMRT took place, which of course will widen the physics program of this gigantic instrument. So therefore, even though we had a series way back in 2002 and then another series in 2008, now we are having the third series on ASSET series on GMRT, and as I said, mainly highlighting the new physics but also with the brand new machine and capabilities. So you will see quite a few talks coming up on engineering as well as the physics of GMRT and particularly the upgraded GMRT in the coming weeks and months. That brings me to just say a few words about today's speaker, Professor Yashwant Gupta. Obtained his MS and PhD in radio astronomy from University of California, San Diego, way back in 1990. And after completing bachelor's degree in electrical engineering from IIT Kanpur in 1985. Since 1991, he has been at the NCRA, National Center for Radio Astrophysics, of the Tata Institute of Fundamental Research, where he currently holds the position of the Center Director. His research work is mainly focused on study of pulsars, exotic neutron stars, and the interstellar medium of a galaxy. In addition, he has significant interest and involvement in instrumentation and signal processing radio astronomy, which I'm sure will come very focused today on his talk. And that really shows up why this machine is, being recognized by the world's largest engineers body. For the years, he has contributed greatly to the building and running of GMRT Observatory, world-class instrument built and operated by NCRA, about 80 kilometers from Pune. He and his team has recently completed a major upgrade of the GMRT, which I said just now. He also leads India's participation in the Square Kilometer Array. You must have heard many times. The SK project, an international collaborative project to design and build the next generation of global radio astronomy facility. Just to conclude, Prof. Gupta was conferred the Sant Swarup Bhatnagar Prize in Physical Sciences in the year 2007. He has also been elected as a Fellow of National Academy of Sciences of India, as well as Indian Academy of Sciences. So with these words, I now invite Professor Yashwant Gupta for his colloquium.
Thank you, Satya. Thank you for all the background and for your kind words, and also for giving this opportunity to talk about the work that we are doing at NCRA, both from the historical perspective and more specifically about what we are doing right now, which is the upgraded GMRT. And also agreeing to have a series of these asset colloquia where other colleagues from NCRA will then cover in more detail some of the specific aspects of the upgraded GMRT, which I will only have time to touch very briefly in today's talk. And that is because I am going to talk a little bit more widely. And it is indeed a very... That is because I am... Okay, I guess there was some echo. And it is indeed a very special moment to look back at the history of the group. And you've heard the reason already from Satya about the most recent recognition that we have got. But it is also equally an opportune moment to pay tribute to Govind Swarup, who started all of this, but left us recently. And in some sense, what we are going to talk about today is basically the legacy that he has built up over the years. So this is the outline. As you can see, it's a skeleton, and I've deliberately not described what those milestones are. So it is, but and partly to keep a little bit of suspense. But all the milestones, since this is a description of work in time over many decades, all the milestones are achievements in certain points of time, and we'll see what they are. Also, since this is a description of the collective effort of a very large number of people who worked in the group over 50 years or more, it is hard to give individual credit in this kind of a description. So I have actually deliberately will not mention any specific names except to refer to us as a team or a group, except for one name. And I will also not have any slides which refer specifically to some particular paper or some particular publication, as is the case in a more pedagogical presentation. And so with that, I will start with the prologue. So it was 1952 when Professor K.S. Krishnan, who was the founding director of NPL, became interested in seeding radio astronomy activities at the National Physical Lab. And at that time, a young student from Allahabad just finished MSc by the name of Govind Swarup. He had joined him, and he appeared keen to take up this activity, which was completely unknown at the time in India. So Krishnan sent Swarup off to Australia to work under some of the most renowned experts in radio astronomy at that time, in the group of J.L. Pawsey at the CSIRO. And indeed, Swarup made good use and worked with many of the experts and got a very thorough grounding in the basics of how things are done in radio astronomy. In 1956, Swaroop moves to the USA and he joins Ron Bracewell at Stanford for a PhD. And at the end of which, he is now a mature radio astronomer, understanding both the techniques and the science that can be done. And after finishing his PhD, he takes up a faculty position at Stanford. But in the back of his mind, he has the wish and desire to return to India and work. And that leads us to that first milestone, which is the birth of radio astronomy at TIFR. So from 1961 onwards, Swaroop and three other Indian colleagues in the US start correspondence with groups in India for returning to start radio astronomy activities. And amongst the various institutions that they approach, they get a most favorable response from Homi Bhabha at TIFR, who offers them positions to come and join and start a group. And here you see the telegram sent to Professor Swaroop by Homi Bhabha, saying that we have decided to establish a radio astronomy group at TIFR, and then follows the letter with the detailed offer letter to Swaroop. And in early 62, Swaroop is the first amongst this group of four to accept the offer for joining, and that's his acceptance letter that you see there. And he then in March 63, he returns to India and takes up a faculty position at TIFR. And that's how the Radio Astronomy Group, which I will refer to as RAG at TIFR, is born. And we now move to the first of the milestones of this group, which is the first project that Swaroop and the Radio Astronomy Group took up, which was to use 32 antennas from the Potts Hill Array, which is the place where Swaroop had worked with Posse in Australia and had got Posse to send them over to be used in India. And they took that, they made an array where the receiver systems and all the electronics was developed by the Radio Astronomy Group in-house. And this array was set up in Kalyan, the same Kalyan that we all know as a very busy and bustling suburb of Mumbai today. And it was a cross array with north, south, and east, west arms. And you can see a picture of it when it was just recently assembled. It worked at 610 megahertz. It was built quite quickly within 2 years, 64 to 65. And it's interesting to ask where in this place called Kalyan today was it located. And I did a bit of research, and it turns out, and there's only one person today who sort of remembers where it was. And so there's an old abandoned airstrip used in World War II by the Royal Air Force as a stopping point. It's located about 12 kilometers or so from Kalyan station, it was in the corner of this abandoned airstrip that they got the land to set this up. So I tried to Google it, but I couldn't quite find exactly the airstrip, and otherwise I would have put up a picture showing where this first milestone was achieved. But the Kalyan radio telescope was used for studying the quiet and active sun at 610 megahertz, and it produced some very interesting results where there was clear detection of enhanced solar limb brightening of the sun, as well as the direct evidence for a 1,000,000-degree temperature of the solar corona from these observations. And from there, we move to the next milestone that this group achieved, which was the Ooty radio telescope. This was conceived of in 63, even as the work on the Kalyan radio telescope was going on. The motivation here was to use lunar occultations to provide accurate size and positions of large number of radio sources to test cosmology models. And there was a way in which you could do this and distinguish between steady state and Big Bang cosmology by this kind of a careful study of a large number of radio sources. But you need enough collecting area to make a sensitive telescope that can detect enough number of such radio sources. And the way Swaroop and team overcame the challenge of building a large collecting area was to make it into a long cylindrical paraboloid rather than a large parabolic dish. And but the telescope was still quite large. It was the effective collecting area of 130-meter size dish, which is significant for those days. And the second innovation that they did was to mount this on a hill and make it a long elongated structure mounted on a hill where the slope of the hill is equal to the latitude of the place. And this is akin to having an equatorial mount. That is, you need to then just rotate the antenna along one axis in order to follow sources from rise to set, and that makes the structure simpler. You don't have to steer it in two directions. The actual north-south movement of the antenna it was achieved by an electronic steering of the beam. And so what happens is that along the axis of this paraboloid that you can see here is an array of dipole antennas which pick up the signal. And so there are 1,056 dipoles which are picking up the locally generated voltage. And then you can combine these voltages in different ways with different phase shifts in order to make the beam produced to be steered north-south in different directions. And so this was how it was done. You can also, of course, combine them with multiple such phase shifts to produce simultaneously many beams which can point next to each other and cover a larger area of the sky. And so this was built, and it operated at 327 megahertz. In the original version, the original design, it had a modest bandwidth of 4 megahertz. But with the time, that has been expanded and increased to larger bandwidths. And so the telescope actually did make those measurements that it was built for. It measured the angular size of large number of sources, and it actually provided evidence in favor of the Big Bang cosmology. It also did many other kinds of studies, because when you build a 130 meter size antenna, there are many other things that can be done. And so it has been used extensively for various studies, from radio galaxies, quasars, pulsars, radio recombination lines, and then both the interstellar medium, the interstellar plasma, as well as the solar wind or the interplanetary plasma. And it's really a tribute to the initial engineering that went in to build this, that it is still functional after 50 years. In fact, it is right now undergoing a major upgrade, which is getting close to be ready for use. And so we still hope and look forward to a much longer life and productivity from the Ooty radio telescope. And it is heartening to see this, that it actually got this recognition when India issued a postal stamp to honor the Ooty radio telescope. We moved from there to the next milestone, which was the Ooty synthesis radio telescope. And this was basically an extension of the Ooty radio telescope into an array. And what was done by the group, and this was their first experiment in aperture synthesis techniques, where you build an array of antennas and then combine the signals from them in order to synthesize an effective antenna with a much larger size. So in this case, the extent of the array was 4 kilometers by 2 kilometers. The array had the Ooty radio telescope as the dominant antenna. And then there were smaller antennas that you can see here, which were all cylinders again, but much smaller than the ORT. They're actually called baby cylinders. And the biggest of these was still reasonable in size, 92 meters by 9 meters, the Muthurai cylinder, which actually still exists. And the others, which were of slightly different sizes and spread out in this kind of a geometry. And this was also operating at 327 megahertz. And it, though it was a relatively short-lived facility, in the sense that it was difficult to maintain this over a long period of time due to various reasons, nevertheless, it produced some interesting results about specific radio sources, some of which are shown here, including some very interesting sources, very steep spectra, and some which have with the peculiar associations and so on. And more importantly, it provided the radio astronomy group with valuable experience in building and operating a synthesis array, which is not, at least in those days, was not such an easy task. And it also provided the appropriate launching pad for um, the next project, which was the Giant Meter Wave Radio Telescope. And the GMRT, which was motivated in the early 1980s, where the main motivation was the fact that though radio astronomy started at low frequencies, over time, most of the large facilities in the world had moved to higher frequencies for a combination of reasons. And there was a gap for a good, high quality, sensitive, low frequency facility that could complement the facilities working at higher frequencies and be able to address a set of science problems which were otherwise not reachable and were best studied at meter wavelengths. And so this first concept in 1984, it started again with the Ooty experience to propose large cylinders, but then it soon evolved to a design which had 34 antennas of 45 meters. That's by 1986. Project was cleared, funding secured by 1987, but the funding was a bit less than what one would have liked, and so it allowed for only 30 antennas to be built as compared to the original plan, but that was still a substantial number. And the construction started in 1990, first antenna erected in 1992, and the first light observations of the interferometric kind, which were with the stable receiver system, were 1997 to 1998, and it was released for worldwide use in 2002. And if you take a quick overview of the GMRT, as I said, there are 30 antennas, and they are spread out in this kind of a geometry. So there are 12 antennas in a compact 1 kilometer by 1 kilometer area. And the remaining are spread out roughly in a Y-shaped structure along these three arms, going out to a radial distance, which is a bit over 14 kilometers. And this then allows you to synthesize, as far as resolution is concerned, an antenna whose diameter is close to 30 kilometers. And the original GMRT, what we call now the legacy system, was designed to operate in these 5 frequency bands with the range of frequencies as given here. But in this, because of the limitations of the kind of electronics that could be done at that time and was affordable, the maximum bandwidth that you could extract at any time was limited to 32 megahertz. So you would have to choose which 32 megahertz you want to observe while observing at any one of these frequency bands. And the GMRT offered an effective collecting area, which is 30,000 square meters at the low frequencies, which tapered down a bit to 20,000 square meters because of the reason that the reflecting surface of the GMRT was designed with a mesh, and that becomes a little bit leaky to the higher frequency waves. And that's, I'll talk about a bit more about how that design was done in a moment. And it was also designed, again, with some good amount of foresight to support 2 modes of operation simultaneously. One is, of course, the interferometry or aperture synthesis, where you want to synthesize an antenna with a much higher resolution. But there is also a mode which is very important, where you just want to add the signals from all the antennas to make it just look like a big bucket collecting more signal. And so you don't have to do the complicated processing that you do in interferometry. On the other hand, you can keep the data at very high time resolution, and you can get a very pointed beam pointing to specific targets. These, in this case, those are the kind of targets such as pulsars and other kind of transient sources where you would like to record data with high time resolution. And so that's a complementary mode to making images of the area of the sky that the antenna can see. And this again had 2 submodes, which I can't go into in this at this level of description. But again, these have proved useful for different kinds of applications. And this is a picture showing that central 1 kilometer by 1 kilometer region. Google will give you all this, and you can just make out the individual antennas, and you can see that they are spaced with some kind of a random separation. These are the ones which are the closest, which give you the shortest baselines. This is the main central building, and the signals from all the antennas are brought by optical fiber to the receiver room here, which converts the signals back to electrical voltages, and the rest of the processing, which you will hear from colleagues in later ASIT colloquia, is all done here. Right here is the control room from where the entire observatory can be controlled. Everything can be configured, everything can be monitored, and long observations of several hours can be run by just one single person sitting in the control room and manning everything. And there are some unique features about the design of the GMRT which make it special. One is, of course, this configuration that I described with the combination of a central compact array and these Y-shaped arm structures, which gives you optimized sensitivity for both compact and extended radio sources. And that's been something that has allowed it to be used for a wide variety of imaging experiments. And the choice of the observing bands was again optimized originally for studying redshifted hydrogen. So the rest frequency of hydrogen falls in the highest frequency band of GMRT, 1420 megahertz is that frequency. And then when you look at faraway objects in the universe which may be emitting this line, then due to Doppler effect, it is shifted down to lower frequencies. And if you take it down all the way to the lowest band, 150 megahertz, you're looking fairly long back into the universe if you detect a neutral hydrogen signal at that frequency. And once again, it was optimally designed. So this reflector that I talked about was really a unique design. It was called the stretched mesh attached to rope trusses concept. And it was optimized to really give the best performance at this range of frequencies that I just talked about. And that's one of the reasons that if you try to use GMRT at the highest frequencies, then you don't get the most optimal sensitivity, because sensitivity begins to fall by that time. And it had a few other firsts. It was one of the first array telescopes to use optical fiber to connect the antennas. Previously, the voltages from the antennas would be brought back either on waveguides or over RF communication links, which would have their own problems of reliability and phase stability and so on. And here it was decided to use optical fiber for the first time, bury it 1 meter underground so that the temperature fluctuations are minimal and you get stable phase response. It's not easy to do that in any locality, in any sort of, mostly in any region in India, to be able to bury fiber for 20 kilometers without running into obstructions. But this was done and it has worked well. So of course, there were initial challenges in trying to make this new concept work reliably, but the engineering team understood and innovated and were able to make this optical fiber system work reliably. And as I said earlier, it was one of the first interferometer arrays to support simultaneously the beamformer operation along with interferometry observation. And it was part of the basic design, and it allows us to simultaneously observe pulsars and do imaging observations. And I don't have time here to talk about what kind of very interesting science results that mode has allowed us, and hopefully that may get covered in one of the subsequent ASIT colloquia. And so just some individual milestones in this building of the GMRT. So this is when, you can see this is when the first dish went up. And you may wonder why the dish went up in the night, but that's, it's a long story of what happened. But this is from that first moment, 1992. And this is an interesting one. This is the first record of a received astronomical signal of the GMRT, 1994, just using a single antenna. And this is the more traditional first record, which is from the array with a certain number of antennas being correlated. And you can see the correlated signal, which tells you that the whole electronics chain is working properly. So this is 1997. And after that, this was extended to cover all 30 antennas and make it into a final system. And that led to this point where on 4th of October 2001, the GMRT was dedicated to the world scientific community by Chairman of TIFR Council. And since then, it's been opened and used by astronomers from all over the world. And this is a representative slice, and not the latest one, but a representative one, but nevertheless still fairly accurate, with about 50% of the PIs of the proposals coming from India, and about the remaining 50% coming from a large number of countries all over the world. And it is also typically oversubscribed by a factor of 2 or more, which means that the request for time in every 6-month cycle is 2 times or more than the amount of time that we have available to schedule during that cycle, and which means that there is a fair bit of competition to get time on the GMRT. And it has been used for a vast range of different science topics, which I won't be able to go into today, but all the way from studying the sun, even looking for extrasolar planets, radio emissions from extrasolar planets, all the way through different kinds of objects, pulsars, supernovae, quasars, gamma ray bursts, and of course neutral hydrogen, and radio galaxies, and all the way to cosmology and the epoch of reionization, attempts to detect signal from the epoch of reionization. In addition, all sky surveys, such as the 150 megahertz TIFR GMRT sky survey that was done a few years ago, which really was at that time a frontline survey at these low frequencies. And the consequence of all this is many interesting new results reported every year, about close to 50 papers now in a steady state mode coming out every year in refereed journals based on GMRT data. And that then takes us to beyond GMRT, which is the next milestone, which is the upgraded GMRT. And so even as the GMRT started working fairly well around like 2005, 2006, the group realized that we should start thinking of a next move, which is to upgrade it so that it remains competitive in the long term, and because there were other low frequency facilities that were being planned and coming up. And so first of these concepts and initial brainstorming and thinking started around 2008, and slowly some amount of initial prototyping and design work was done. And serious work started around 2012 after the 12th plan proposal for funding the upgrade was approved. And that work then spanned a good 6 years or so. And it was towards the end of 2018 that it was completed, though there were early partial releases from 2016 onwards, which means that as different aspects of the upgraded GMRT got ready, we released it for users to start using them. But the final system was completed with the end of 2018, and it was formally inaugurated in 2019. I'll talk about that in a minute, and was available from April 2019 to the entire user community. And what were the main targets or goals for the upgrade? These were identified as follows. One, as I showed before, that that there was spot range of frequencies that the legacy GMRT was designed to cover. And it was felt that we could try to do a seamless frequency coverage without any gap in the frequency coverage, if possible, from 50 megahertz to 1500. And that required a completely new feeds systems and receiver systems, which you will hear about in the next talk in this series. And also to use the opportunity to improve the quality or sensitivity of the basic receivers itself, which is just putting to use the best technology that you can work with. And the other big step was to see if the instantaneous bandwidth can be increased from the 32 megahertz that I talked about earlier by more than a factor of 10 to 400 megahertz, which was again a fairly giant step. And that required again radical modifications to the entire receiver chain, all the way to the backend receiver, which receives the signals at the central station and digitizes them and then processes them. It needs to now process 400 megahertz from 30 antennas in dual polarization mode. And this again, you will hear about in one of the later talks as to how this was done. And then it was also decided to take the opportunity to revamp things which would anyway face danger of obsolescence after some time. So that included a new server system, going in for the brushless drive technology and with the new server computer and so on, and also revamping the entire monitor control system and building a new one, which actually happens to be in synergy with what we are doing for the SKA. And matching improvements in offline computing, archiving facilities, all of which are needed when you are going to now be swamped with much larger volumes of data coming from this upgraded data stream. And in addition, also to take care of mechanical and electrical systems, some of which again, issues of obsolescence and degradation, some improvements and additions. And so all of this was folded in, and this was the package that we went with. And one of the main challenges for us was to do this without shutting down the observatory, because we did not want to say that, well, the GMRT is down till we finish the upgrade. We are not going to have it available for users. So we did this while keeping the observatory available in the existing legacy mode, even as the upgrade was done. And like I said, as the upgrade got done in parts, then it was made available to the users while keeping the legacy system working. And this gives you a very quick schematic of the difference. So these are those 32 megahertz wide bands that you could place in the legacy GMRT, again with some restrictions. You could not place them anywhere in this wide pink range, which is the range of the frequency coverage of the upgraded GMRT. And as you can see, we've managed it actually from a bit below 120 megahertz, closer to 110, all the way to 1450, except for the gaps that you see here, which are basically because the radio frequency interference from man-made sources here is so strong that it just doesn't make any sense to try and operate. This in particular is the mobile band, these things without which we cannot live anymore, and but they really mess up things at the observatory. So the upgrade was then targeted to give this kind of an expected performance. So what this shows here is the RMS sensitivity that you would get in an image made from a 9-hour synthesis run in observing at the different frequencies which cover the GMRT band. And so the lower this number means the lower is the noise in the image and the more sensitive is your image. And you can see fainter sources. And so the blue circles mark the performance of the legacy system, and the purple circles mark the performance of the upgraded system. And this was the target. As you can see, if you compare it with the other facilities which are either operational or just coming up around the globe, we remain one of the most sensitive facilities with the upgrade, except for these star points, which are from the square kilometer array projected sensitivity, which is yet to be built, is being now finished the design and starting talk about construction. So this was the target, and by and large, we've achieved that. We do get much higher sensitivity with the wideband upgraded GMRT systems, and it also gives you this much more agile system where you can, because of the larger frequency coverage, you can look for redshifted hydrogen lines at a much wider range of redshifts, and that has already been used to very good effect in some of the recent results, which again I hope you'll hear about later on. So just to put this in a nutshell, the upgrade touched everything from wideband RF electronics to improvement in the optical fiber system to transport these wideband signals, to next generation digital processing, revamped servo system, and smart interference rejection. I'll talk about that a little bit more, and started to open the door to exciting new results, which we are now seeing. And I'll just give you just one example, because there really isn't time, and hopefully colleagues will show some more of that in the later talks about the improvement in the sensitivity when you compare the legacy system with the upgraded system's image of the same part of the sky. And you can see clearly the improved sensitivity in terms of the ability to see much fainter and many more sources. So, of course, this was not without its challenges, and the technological challenge, of course, was the technology to do all this, which you will hear about in later talks. The second challenge, which was, like I said, to keep the existing GMRT working without shutting it down, was an interesting one. And so it involved technological design choices such that you could allow the signal from the legacy system to flow in parallel with the signal with the upgraded system. And both were processed, are still being processed in the central building. And you can then simultaneously, get the performance of what the legacy system used to offer, at least the minimum that it used to guarantee, and the new wideband system. And in hindsight, this has proved extremely beneficial, all the way from first comparing whether the upgrade is actually giving the improved performance to even today where we find differences in the way we see results between the legacy and upgraded system, which has allowed us to improve the upgraded system. And the last was that you need, how do you do this while running the existing system? So we had to change the operations model. In fact, for a few years, we became more like an optical telescope where we were observing only during the nighttime and the weekends and giving all the daytime to the engineers so that they can go in and put in these changes one by one on the different antennas for the different bands that we were covering. And so that's how we ran for quite some time. Today now, when most of the upgrade is now done pretty much, we are back into the normal schedule where we have no observations only on the maintenance days, and otherwise we are running 24/7. The largest, perhaps, of the challenges, which still remains with us, is to control the radio frequency interference from man-made sources. And this will hopefully be covered in one of the talks. And so again, I won't go into this in detail, but this is one of the biggest challenges in making it work. And there's a couple of other interesting things that happened once you again build a facility like the upgraded GMRT. It has applications beyond what you would normally think in astrophysics. And this is one example where we were actually able to use it as a very sensitive probe for as like an Earth station to pick up very faint signals coming from the ExoMars mission. So this was a collaboration between us and NASA, and NASA was working along with ESA for providing ground support for this mission. And they approached us to use the phased array mode of the GMRT to pick up this tracking beacon that the lander module would emit when it makes this critical journey through the Martian atmosphere to make the landing. And this may remind you of Chandrayaan 2. And so we were able to run this successfully, pick up that signal, and track its Doppler as the craft descended, and then check whether this is how it should be as per the expectations. And it turned out, like Chandrayaan 2, that it was not, and that the signal was lost just about 30 or 40 seconds before the expected touchdown time. And this is being relayed live from JMRT to the control room in Germany. And it was something that literally stopped them in the tracks because, like Chandrayaan 2, it actually crashed because of a miscalculation in its, the way the trajectory was worked out. But the important thing is this is like picking up your mobile phone. If you ever take it to Mars and talk from there, the GMRT can pick up that signal. So this UGMRT finally inaugurated on the most opportune of moments, and we were really happy that we could couple it with the 90th birthday of Govind Swarup, and he did the honors. You can just about make him out in this on the screen here. He's standing there ready to press the go button for inaugurating the UGMRT, and the already even as it was being inaugurated, there were new results that were flowing from the upgraded system. And like I said, we'll hear some of them in the subsequent talks. And even after that, we have been doing some further technological improvements and new modes that are being implemented to further enhance the capability of the upgraded system. I come now to a different kind of a milestone, which is actually the birth of NCRA, which actually, strictly speaking, belongs somewhere in the middle of milestone 4, because it happened while the work with the GMRT was going on. But I didn't want to break the flow of the building of the GMRT and its upgrade, and so it stands a little bit out of sequence. But this was 1994. And so the basically since 1980s, the group had grown substantially from the relatively small group that Govind Swarup started with. And the work of the major GMRT project caused a significant increase in the number of people who were now working in the group. And in addition, of course, the group had to now split, and a good number had to move to Pune because that is where the site of the GMRT was finalized. And so now there were multiple locations, two major projects, and a lot of things to be managed with a large number of people. And so this activity now had grown large enough to warrant the creation of a separate independent national center of TIFR. And that's when the Radio Astronomy group formally transitioned to what is now the National Center for Radio Astrophysics. And that, I think, was an important milestone because it gave NCRA a bit of its own identity and the specialization of the work that we do and some freedom in how we do it. And that is also an opportunity for me to just very briefly give you the current organization profile of NCRA, where we have a good number of faculty. We could probably have more. And we have three different streams of faculty, which allow us to cater to supporting the observatory as well as developing new technologies for radio astronomy. And we have a good number of PDFs and a decent number of students now, which was not the case in the early days, and a thriving many areas of research covering a wide spectrum. In addition, we have very strong technical strength. There's close to 150 engineering and technical staff, regular staff, and then lots of the project staff, mostly at GMRT, some at the Ooty telescope, and few at Pune campus. And again, there's a major strength in various areas of technology, from radio frequency electronics to optical fiber, digital electronics, signal processing, servo and mechanical engineering, software and computing. And that is what allows us to support these two large facilities and also aim for a larger presence in the global scenario. So with that, I'll just move to the last, which is actually a set of smaller milestones, which just some things to celebrate. Coincidentally, most of these have come over the last year and a half. But I just wanted to bring these up that we were awarded recently the Zubin Kimbhavi Award of the Astronomical Society of India, which is given every alternate year for observational and instrumentation work in astronomy and allied fields. And it was given to Team GMRT for the work done for the upgrade specifically. And this was actually one of the first major compliments for the entire team that has done this work. And more recently, earlier this year, the American Physical Society chose us as NCRA to be in the select list of institutions to feature in the annual meeting of the APS, which normally happens in March 2020. And they commission a film highlighting the achievements of the particular organization that they choose. And that is shown live at various times during the APS movie. And of course, it's available now to watch on YouTube. And this, if you get a chance, I would encourage you to have a look. It's very nicely done, and it really brings out the work and achievements of the entire group, with, of course, the GMRT being the main highlight in this film. And this one, which you already heard about just last week, we were given this special status, we meaning the GMRT facility, the IEEE milestone status, which, as Satya already mentioned, is only the third such milestone in India, which I think is a bit of a shame because I think there are other achievements in India that are worthy of this. But that said, I mean, these go back to the achievements of J.C. Bose in showing generation and reception of radio waves almost a year before Marconi did it, and C.V. Raman for his Nobel Prize discovery. And so given that, notwithstanding that I think there are other facilities in India that deserve this, it is still a major international recognition for us. And it's a very fitting tribute for the entire group, and a special tribute to Govind Swarup. And I'll just flash this. This was the congratulatory message that the president of the IEEE put out on this occasion. I won't read this in detail, but it just tells you what's the importance of the IEEE milestone, what does it recognize, and what he says about the work done by our team. Okay, then I come towards the end in just looking a little bit at the road ahead. Um, uh, and Here's just a quick snapshot. On the science front, our main emphasis at the moment is, of course, to get as many quality new results with the upgraded GMRT. That's really the current focus, and it's beginning to happen. You will hear about that in later talks, but there's certainly much more that can be done. And from the engineering side, as I said, we're looking at additional features to the upgraded GMRT in the next 2 or 4 year kind of time frame. And some of them are already again happening. The VLBI is almost getting going, and even the improved field position system is getting installed on antennas. And then looking on a longer term horizon, there are these two things that we are looking at. One is to ask that can we expand the GMRT to become an even a more sensitive and more useful facility on a time scale of the next 5 to 10 years. And there are different options that have been explored, which talk about more collecting area with more dishes, whether the dishes should be on shorter baselines, longer baselines, or an optical combination. These have been objects of discussion and study, and also the possibility of giving each dish a wider field of view by going in for the focal plane array technology, which is the equivalent of having multi-pixel feeds at the focus. And it's the radio astronomer's equivalent of a CCD array or analogous to that. So all of this is under consideration. There is also this under progress, the participation in the large projects, and the one that we have been aiming for is the SKA, which is going to be built over the next 10 years time frame. And we've been participating in the effort there, where it's a nationwide effort with NCRA leading the work that's happening. And we've contributed significantly to the design phase. We had the lead role in one of the work packages, and we are planning for significant contribution to the construction phase, which is now under finalization as to what all we may be able to take up. And much of that is being done with the hope that we can synergize this with in-house facilities, national level facilities, and growth options that we see within the country wherever possible. And the science case for what the Indian community would like to do with the SKA has been fairly well developed, and the community is growing. Today, we have more than 20 institutions from all over the country that are members of the SK India Consortium, and we are looking forward to working with all of them towards the next generation. So to just summarize with just my closing thoughts, that as you've seen, the Radio Astronomy group at TIFR started by Govind Swarup 63 has come a long way from those early days. And with the achievements of building facilities like the Kalyan telescope, Ooty telescope, the Ooty synthesis telescope, and GMRT, and then now the upgraded GMRT, as well as the accompanying growth in research and wide range of topics that is happening, we are now a mature and well-recognized group on the international stage. And that is seen now very clearly. And so we now, even as we look at getting the full benefits from the upgraded GMRT, we are also looking ahead to what would be the best growth avenues for the future. And hopefully out of all of this will emerge the best way forward so that we can keep the legacy of the Radio Astronomy group of TIFR at the highest level. And with that, I stop. Thank you.
Thank you very much, Yashwant. Oh, that's a nice animation.
Yes. It's a symbolic. People often don't realize what the NCRA symbol means.
Yeah, that's right. Thank you very much. This is a fantastic colloquium, really literally spanning, almost like, more than 55 years of the story, try to put it in 55 minutes. And, but also, brought into various great technological advances that you and your group has been part of. At the same time, also did the science that the whole world recognized. So there are, of course, quite a few questions, and there will be, I'm sure, more questions. So I request people who are on Zoom, if you prefer, you could just unmute yourself and go ahead and ask your questions. By the time the people join in, there are a couple of kind of informations or comments in the chat box. If you have access to that, you can have a look.
Yeah, I saw that Arnab is saying that he can see the airstrip. I tried looking for it. That'll
No,
be
in
nice
fact,
to.
I did click and it does show this is Kalyan airstrip near Naivel.
Yeah,
Ali, I forgot that
that's
exact.
good. So next time such a talk is given, it shall be shown.
Nevali.
Yes, yeah.
Uh,
That's what Islur is. JD Islur is one of the oldest surviving members of that team that built it, and he says that that's where it was located. Yes.
yeah, it also shows BARC very close, just towards the east.
Yes. There's land that is owned by DAE over there.
Must be BAE. Okay. Another comment that was also posted by Aniket, you must have also seen about this
Yes.
Kalyan land. So that those are the comments. Uh, so okay, if there are any questions on the Zoom, please ask. By the time, let me take a couple of questions from YouTube. This is Abhinav Chaudhary. Of course, he's trying to take you from radio astronomy to neutrinos. What are radio neutrino telescopes and how they are used in the detection of ultra high energy cosmic rays and neutrinos?
Neutrino radio telescopes.
Yeah, are there one?
Maybe some of the colleagues who are more into the neutrino world would have a understanding. I'm just trying to think.
It's a radio neutrino telescopes.
Okay, that's a bit of a new thing for me. I don't know if any of the other colleagues have an idea of what. I am scratching my head to think of.
Eh, Yashwant,
Yeah, yeah,
it is about neutrino shower,
yes.
neutrino producing shower in the atmosphere or something, and that from there you get the radio waves. Like air
That,
shower, you can get a
yes,
radio wave.
yeah.
That is the type.
Okay, but usually the shower doesn't produce. You pick up different signals from it rather than radio waves, right?
No, not the radio waves from the cosmos. It is the international. This is within the atmosphere. Whatever was produced,
Yeah.
this is the radio.
Okay.
Yes, okay.
Another question from the same, how GMRT helped in observation of the biggest explosion in the history of universe, the OP, I can't even pronounce it, OPQS supercluster explosion.
Yeah, so the GMRT has this unique ability to be able to do very sensitive imaging at the low frequencies. And a lot of that kind of imaging has been used to study structure in the remnants of such explosions, not just this, but even for other explosions such as the gamma ray bursts and supernova explosions and so on. And the ability to detect the signal from the remnant allows you to then characterize the structure of the remnant and hence infer about the energy of the explosion that produced that, in very briefly speaking. So you're not actually observing the explosion, you're observing the aftermath of the explosion much, much later.
Okay. Are there any more questions to Yashwant? Yashwant, you mentioned about the, in the future, future work that is waiting for even the upgraded GMRT is in terms of the kind of multi-pixel, uh, you know, wider field of view devices. So can you kind of say a little bit more? You said it is akin to kind of CCD of an optical.
Yeah, it's only a very rough analogy. So what happens is the normal feed antenna that we have at the focus is like a single pixel element, and in order to have the ability to cover the aperture, the focal plane, you need then more of these basic elements, which are mostly dipoles that are put. And so you make a grid of such dipoles. And then what you need to do is to combine the signals from these dipoles in order to fashion the final beam, which, when seen along with the reflector dish, is actually pointing in a slightly different direction in the sky than the central beam. And so you can then get a array of such beams within the primary beam of the antenna, which then allows you to cover a larger area of the sky in one go, simultaneously, while pointing the antennas in that direction. And so this it's therefore it requires both electronics, where these individual dipole elements have to be designed very carefully so that they don't have any unwanted crosstalk between them, and then the algorithm which allows you to combine the voltages from these in order to fashion the final beam with the right characteristics, with as much wide range of frequency, that is the bandwidth, that as you can manage to do. And then, of course, now you're getting from each antenna amount of data that is, if there are n beams that you have fashioned, then that amount of data is n times what you were getting earlier. And you're getting that from each of the antennas. And then you have to know how to transport it and how to process it. So, that complexity grows downstream as you go. But that is now possible with the current technology. And there are antenna arrays which are being built and also producing results now with this kind of techniques.
If I can, of course, there's one comment again waiting, but if I can just ask a follow-up question to what you answered just now. Maybe this is a question which will probably go later to Ajit and others, but just at the back end, given the fact that now you have very, very high performance, let us say, field programmable gate arrays in the RF areas, they're called RF system on chips and so on, with a fantastic amount of data throughput capabilities. So even though, of course, they might generate certain noise, which may not be a good thing for you at the focal plane, but is there some really big level of change of the instrumentation, especially electronics, even in the upgraded GMRT or beyond, going more towards from discrete digital circuits to, let us say, programmable digital circuits?
So certainly, I mean, and I will leave that for Ajit to answer in the later colloquium, but certainly that move has already happened, that even in the upgraded JMRT, there's a certain amount, a good amount that is done with the FPGAs as compared to discrete electronics. And that transition happened a long time ago. The other transition,
your voice is a bit low.
Yeah, like I said, that what I was saying is that transition has happened in radio astronomy quite some time back, where discrete electronics has been replaced by FPGA-based electronics, especially downstream as you do the processing. In fact, and I didn't have time, and this is what the team mates, team colleagues will cover later, that we've also gone in where a lot of this has been moved to the equivalent of a high performance computing platform in order to do the signal processing, as compared to either doing it with discrete electronics or even with the FPGAs and DSPs. So there is another paradigm where once you get this data, if you can manage the data rates, get it into a cluster of computers with GPUs, then you can do a lot. And that you will hear how we've done the backend for the upgraded GMRT.
Okay. Actually, Yashwant, towards end of your answer, your voice has become much better. I think there is some certain position. Otherwise, your voice is a bit low.
Okay.
So I want you to kind of position yourself at that place.
Sure.
A couple of questions. Maybe Aniket, are you there? Would you like to kind of make this comment? Aniket, can you hear me? Can you unmute and ask this question? Okay. So maybe let me then ask. Okay, one of the question before I go there is, what is the reason for the Y-shaped array of antennas, and why Y-shaped? This is from Ashish.
Yeah, so that's a slightly more technical issue, that finally when you are trying to simulate an extended array or the performance of an array by just using a limited number of antennas which are located within that geography, you need to decide what should be the optimal placement given in antennas, so that you can get the best coverage in order to be able to synthesize that beam with the highest fidelity. And that then is a bit more technical, but it basically boils down to asking, in some sense, how many non-redundant vectors can you get from the pairs of antennas over the n antennas, and as many of them as possible, and including the fact that that effective vector changes as the Earth rotates, as seen from the source. So like I said, that's now getting a bit technical, but that is the basic requirement. And you can then do the simulation which says, given n antennas in a certain region over which I have to spread them, what should be the optimal, what are the optimal configurations in which you will get the best performance from the n antennas. And the Y-shaped structure happens to be one of them. A spiral is another, and there are others, but Y-shape is one of the common ones, and that is the one that was adopted for GMRT, except for some local variations where, because of the non-availability of land and other geographical constraints, you can't exactly follow the Y-shaped structure.
Okay, let me read Aniket's comment. Since this is a talk on Radio Astronomy Group's history, it may be good to mention how GMRT was built using modest resources and completely indigenous engineering support. So do you want to comment about that?
Yeah, so certainly both of those are true. And like I said, the original plan, if there was enough money, was to build 34 antennas, but finally only 30 got built, and so on. And so, but it is really a tribute to the skillful engineering that the group was able to do, which so it's one of the most frugal radio telescopes in the world. When we tell people that something of this size was built with the equivalent of $15 million, people find it hard to believe. And so that required all of this. So I did mention that the antenna structure was optimally designed with that mesh and the support, so that it is as light as possible while still meeting the scientific requirements, and that really reduces the cost significantly for building such large antennas. And so similarly, there were other innovative things tried, and it was all done by the team Radio Astronomy Group. There was only minimal collaboration. There was some collaboration. There was some collaboration with the Raman Research Institute, so you can still say it's made in India, and some small amounts of collaboration with groups outside in other countries.
Okay. There is a question from Dekumar. He says this is not related to GMRT, but in the Mars picture, there were parachutes. How do they work?
I mean, I would hazard that they work in the same way that the parachutes that humans use when they jump off from an airplane work, in the sense that I'm not sure what the intent of the question is. That that spacecraft has some pre-programmed sequence of events that it has to follow based on the data it is collecting.
I meant, is the atmosphere strong enough there on Mars to?
Yeah. So those are the calculations that went into their choice of these options, and it probably is sufficient that it offers certain amount of drag so that it can slow it down. But finally, the main thing comes from the thrusters to slow it down, which were the ones that sort of fired for the wrong amount of duration when the analysis was done.
Okay, Arnab, do you want to ask the question or comment? Okay, he says, I would also like to congratulate GMRT for the fantastic efforts in science outreach with one of the largest science celebrations around in the National Science Day, attracting 25 to 40K participants mostly students, teachers from mostly rural and small town backgrounds.
Yeah, no, that's true. And I didn't have time, so I didn't include that as one of the items, but it is one of the highlights of the outreach that we do, which is not very large otherwise, but this is one of the main events that we all put in a lot of effort, which happens on. So normal science day is observed for one day, but one day is not sufficient for us. It is we run it for 2 days, and the 28th and the next day, and it has now a structure which has grown over the years, where it is not just us showcasing what we do, it is others also showcasing what they do, and that ranges from many of the local schools with the school kids coming and showing their science projects, to colleges showing what they do, and also to research institutions that come and showcase what they are doing. And so it has now become literally a science gathering of the entire region, and we do get colleagues even from a little bit beyond the region. We certainly get colleagues from the Kolaba campus who come regularly and show interesting things to the visitors. We get colleagues from the balloon facility from Hyderabad who come, and certainly institutions from Pune, and even now some from Nashik and so on who come there. And so it is one of the largest gatherings, and it probably won't happen this coming year, but it is something that is certainly worth attending and something that we look forward to.
Actually, maybe we'll take just two more questions. One from Aniket again. He's of course wanted to get a little more details about the GMRT's role, Radio Astronomy Group's role in SKA development.
Okay, so as I said, that we from the NCRA side, we have had, of course, and I didn't bring this out, and it's probably something that I should have, that some of the seed ideas for for having a large project like the SKA actually trace their history back to Govind Swarup. I mean, I had one more section in my talk which I dropped, which were milestones that did not happen, but never mind. And so in fact, from those times, the group has been involved in the thinking and the planning and the work for what is now become and called the SKA. And from our group, we've worked. We are a member of the current SK organization since 2015, with DAE as the official representative. And we have participated in the design phase extensively. Our group, working in collaboration with industry partners, has led the design phase for what was called the telescope manager during the design phase, and is now called the observatory monitor and control system, which is an enhanced role and scope from what the original telescope manager was, is the new work package that it has become. But we led that with working in synergy with industry partners. And there are a couple of other areas where we had shown interest, and we contributed to a smaller extent in some of the signal processing activities. And going forward, we are looking in a bigger way in collaboration with other institutes and partners from within India, such as the Raman Research Institute, Indian Institute of Science, IIA, and some of the IITs and the ISERs, as well as some of the universities, to work together, both to have a significant presence in the science that one would do with the SK, and hence preparing for that by using our existing facilities, such as the upgraded GMRT, as well as taking part in some of the planned construction phase activity, which includes leading the construction of this work package whose design we led. And that has been agreed by the SK that we are the best placed country to lead that work package. And then there are some of the other work packages which involve building of hardware and signal processing for the SKLO, which also we are now part of. So all of that has happened over the last 6 years, from 2014, when we started seriously working in the design consortia.
Okay, so Yashwant, I would like to take this last question because it actually is from a student. And but just before I go there, of course, there's a message from Srirup which says congratulations to GMRT for a whole slew of achievements, and thanks to Yashwant for very well crafted talk. That's from Srirup. So the student has a couple of parts. Firstly, he says he's a final year BTech student, PCE. He says he worked on computational astronomy in detection of pulsars and classification of galaxies in my bachelor's degree. So he wants to get your advice on how to kickstart with the journey towards radio astronomy. That is one advice. The question is, sir, what is your opinion on search of extraterrestrial life using radio astronomy? So these are the two parts of it.
Yeah. Okay. So the first one, definitely, I don't know where you are in India, but I would encourage you to come and visit us, and get more closely acquainted with what happens in an actual radio astronomy observatory and a radio astronomy organization. And definitely, one can then talk and discuss. It also depends on what stage of your career you are in, and
He says he's final year electronics and communication engineering.
yes. So there are different options that you could consider if you want to do more of the core engineering, or if you want to do a mix of engineering and astrophysics. Then there are different options. But I think that's best discussed separately rather than on this kind of a call or a talk. But we'd be happy to do that. So you should feel free to write to NCRA about it. About your second question, I didn't bring that topic up, not because radio astronomy is not used for search for extraterrestrial intelligence. It is considered to be one of the most promising avenues for this quest for detecting extraterrestrial intelligence. And many observatories do that. It's partly because we don't do much of that work at NCRA, at least not so far. But it is true that this is certainly possible. Now, if you ask what are the prospects of a successful detection, that's very much anybody's guess in terms of what is possible. But there are certainly concerted efforts that are made to use radio observatories for searching and trying to find such signals.
Okay. So on that note, we would like to thank on behalf of all of you who are on this call, Yashwant, once again, congratulating him for this latest recognition that the GMRT got. So obviously,
thank you. And I mean, really, this is to all the members of the organization. I mean, really the collective effort here.
And we all, of course, look forward to many such accolades and recognitions for you and everyone in your team. And also, more specifically, we look forward to more detailed subsystems now that are going to be dealt by both engineering and your colleagues on both science and engineering that's going to come up in the weeks and months for next 2-3 months. So with that, thank you once again. Thank you very much, Yashwant. Thanks all of you.
Thank you. Thank you for the opportunity.